Welcome to the next lesson in time-independent perturbation theory. In this section, we will consider the second part of the fine structure of hydrogen atom. The fine structure of hydrogen atom comes also from the spin-orbit coupling. In the last class, we have discussed the fine structure coming from the correction due to relativistic expression of kinetic energy. Here we will discuss the second reason for the fine structure correction, which is called the spin-orbit coupling. Spin-orbit coupling is the interaction of the electron's spin magnetic moment with the magnetic field generated by the electron's orbit around the nucleus. In another way, we can say that it is the interaction between the electron spin and electron orbital angular momentum. Spin and orbital motion of the electron are interacting. This is called a spin-orbit interaction, or L and S interaction. This interaction leads to shift in electrons' atomic energy levels, and this is detectable as the splitting of spectral lines. We can assume this as an internal Zeeman effect. Now consider the electron in the orbit around the nucleus. Now from the frame of reference of the electron, the nucleus, or in the case of hydrogen atom, it is the proton. The proton appears to be moving in a circular path around the electron. It is with respect to the frame of reference of the electron, or in the frame in which electron is at rest. So this orbiting proton will introduce a magnetic field, and this magnetic field B exerts a torque mu cross B on the spinning electron, where mu is the spin magnetic dipole moment of the electron. And this contribution, this interaction between the magnetic field B and the magnetic dipole moment mu produces a magnetic energy minus mu dot B. So this much of additional energy comes as the energy of spin orbit interaction. So the additional term to the Hamiltonian becomes minus mu dot B. So first of all, we have to evaluate the expression for minus mu dot B, where mu is the spin magnetic dipole moment of the electron and B is the magnetic field produced by the orbiting electron in the frame of reference of electron. Now to find HSO, we have to find mu and B. Now first of all, we will calculate the magnetic field B. In the reference frame of electron, the proton is moving in a circular path. So it can be assumed to be a circular current loop. Now at the center of the current loop, the magnetic field produced is by the Biot-Savart law. It is mu 0 I by 2R, where I is the current and R is the radius of the circular path. Here I is equal to current is equal to charge by time. It is equal to E by T, where E is the charge of the proton and capital T is the period of revolution of the proton. It is equal to E by T. Now the orbital angular momentum of the electron, that is in the rest frame of the nucleus. Rest frame of the nucleus is the inertial frame. The orbital angular momentum of the electron is L is equal to RmV, because the electron is revolving around the nucleus. That is the L is equal to RmV is the expression for the orbital angular momentum in the inertial frame. So that is equal to Rm into V is equal to velocity equal to distance by time, that is equal to circumference by period 2 pi r by t, that is equal to 2 pi mr square by t. Now B and L are in the same direction. Magnetic field produced by the proton in the reference frame of the electron and magnetic dipole moment of the electron in the reference frame of proton, the magnetic orbital orbital angular momentum of the electron L and the magnetic field B are both in the same direction. So we can write B is equal to mu 0 I by 2R, that is equal to mu 0 by 2R into I is E by T, that is equal to mu 0 E by 2R into 1 by T. From here we get 1 by T is equal to L by 2 pi mr square, L by 2 pi mr square, or B is equal to 1 by mu 0, B is equal to mu 0 epsilon 0. I am adding an epsilon 0 in the numerator and denominator, epsilon 0 by epsilon 0 E by 2R. Now that is equal to 1 by 2 into 2 4 pi epsilon 0 into E by m c square. C square is coming from mu 0 epsilon 0. Mu 0 epsilon 0 is equal to 1 by c square, that is c square r cube L. Now in vector form, both B and L are in the same direction, so vector B is equal to this scalar, that is this much of quantity into L. So we have found the value of magnetic field B in terms of the orbital angular momentum of the electron. Now next step is the spin dipole moment of the electron. According to quantum mechanics, the spin magnetic dipole moment mu and the spin angular momentum S of an electron is related by the expression mu is equal to minus E by m into S. So putting all these equations, we get HSO is equal to minus mu E dot B, that is equal to minus of minus, that is plus E by m into S dot 1 by 4 pi epsilon 0 into m c square r cube into L, that is E into E square by 4 pi epsilon 0 into m square, m into m square, c square r cube into S dot L. So in this one, these are scalars and this S dot L is the operator. So HSO, or the spin orbit interaction, introduces an amount of energy of this much. It is an operator S dot L. So this equation is obtained in the rest frame of the electron. We have found the magnetic field B produced by the orbiting proton in the rest frame of the electron. It is not an inertial frame. It is not an inertial frame. It is a non-inertial frame, means it is an accelerated frame. So that expression is not correct. So transformation of this equation into inertial frame introduces a factor of half. It was introduced by Thomas and it is called Thomas precision. So the corrected equation is h dash of SO is equal to E square by 8 pi epsilon 0. We have got E square by 4 pi epsilon 0. It becomes here, by converting from the rest frame of the electron to the rest frame of the proton, or from the non-inertial frame to the inertial frame, we have added an additional term 1 by 2. So by multiplying by 1 by 2, we get E square by 8 pi epsilon 0 1 by m square c square r square S dot L. So this is the spin orbit interaction energy. This HSO can be taken as a perturbation to the main energy levels. Now, to find the first order correction to the energy level, we have to select the unperturbed states, a good basis for the unperturbed states. Now, HSO, which includes S dot L, it will not commute with the L and S, that you can prove. So the HSO and the total Hamiltonian H will be including both the main Hamiltonian H0 plus the spin orbit interaction Hamiltonian H dash of SO. If H dash of SO is not commuting with L and S, then total Hamiltonian is also not commuting with L and S. So the spin and orbital angular momenta are not separately conserved because L and S, they separately do not commute with H dash of SO. Thus, the eigenstates psi NLM, that is NL, ML, MS, it is specified by ML and MS of LZ and SZ are not good states because these eigenstates if we use this as the basis of the unperturbed states, then our Hamiltonian H dash of SO, that is the correction Hamiltonian H dash of SO, will not be diagonal. It is not diagonal with respect to this basis. So if we use this basis, we have to perform degenerate perturbation theory, or first of all we will have to find the characteristic equation for the finding the Hamilton first order correction, but it is a very difficult process. So here we will select another basis for the representation of this H dash of SO. So we take this H dash of SO, that is, it contains L dot S. This L dot S commutes with the L square, S square, and the total angular momentum L plus S represented by J, and the Z component of the total angular momentum Jz. So the eigenstates of these four operators, they are represented by N, L, J, Mj. And the eigenstates of these four operators are commuting with our perturbation H dash of SO. So the basis formed by these eigenstates are a good basis to use in perturbation theory. Or we can say that our perturbation H dash of SO is diagonal in the representation of NLJMJ. So by using this basis, we can proceed with the non-degenerate perturbation theory. So using this basis NLJMJ, we will proceed with the non-degenerate perturbation theory. So these good eigenstates NLJMJ are the linear combinations of the degenerate states NL, ML, MS that combines different ML and MS values. And the coefficients of these linear combinations are called the Klapsch-Gordon coefficients, that again you have studied in the theory of angular momentum, the addition of angular momentum. Now we have J square is equal to L plus S dot L plus S, that is equal to L square plus S square plus 2 into L dot S. So we get L dot S is equal to 1 by 2 into, that is this L dot S, that is 1 by 2 into J square minus L square minus S square. So this is L dot S. So our spin orbit contribution H dash of SO is equal to E square by 16 pi epsilon 0. This 1 by 2 is added here, so 8 becomes 16. Now 1 by m square c square r cube J square L square S square. So this is the spin orbit interaction in terms of the operators J square L square and S square. So the first order correction to the energy of the hydrogen atom En of 1 is equal to the expectation value of H dash of SO with respect to the basis NLJMJ. So NLJMJ H dash of SO NLJMJ. That is equal to H dash of SO is this one, E square by 16 pi epsilon 0 1 by m square c square r cube J square minus L square minus S square. So constants can be taken out. E square 16 pi epsilon 0 1 by m square c square can be taken out. Then the remaining will be NLJMJ. J square L minus L square minus S square NLJMJ by R cube, that is this R cube. So that is equal to, now J square operating on this one is J into J plus 1 H cross square. Now L into L plus 1 H cross square. This one S into S plus 1 H cross square by R cube. So we can take the H cross square outside. We get E square by 16 pi epsilon 0 H cross square by m square c square into J, that J into J plus 1 can also be taken out, because they are now constants. J into J plus 1 minus L into L plus 1 minus S into S plus 1. Now the remaining will be expectation value of this term is taken out. So the remaining will be expectation value of 1 by R cube. Expectation value of 1 by R cube with respect to the basis NLJMJ and NLJMJ. So that is En of 1 is equal to this one into minus S into S plus 1 into expectation value of 1 by R cube. Now for hydrogen atom, S is equal to half because there is only one electron. And the expectation value of 1 by r cube is independent of m and s. It depends on n and l. So expectation value of 1 by r cube with respect to nl, j, mj and with respect to nl, ml, ms are same. So this expression already there is a standard result. It is 1 by r cube is equal to 1 by l into l plus half into l plus 1 into n cube a cube. So it is equal to n of 1 is equal to e square by 16 by epsilon 0 h cross square by m square c square j into j plus 1 l into l plus 1 minus s into s plus 1, that is 3 by 4 by l into l plus 1 l plus 1 into n cube a cube, that is equal to n of 1 is equal to this one into minus 3 by 4 by l into l plus 1 into l plus 1 n cube a cube. Now we are converting this in terms of n. A is equal to, that is bore radius, A is equal to 4 by epsilon 0 h cross square by m e square. Therefore this n of 1 is equal to e square by 16 by epsilon 0 h cross square by m square c square. Then m e square, that is this a cube, that a cube becomes m 1 by a cube is here, a is this one, so 1 by a is m e square by 4 by epsilon 0 h cross square whole cube into 1 by n cube, the remaining, the quantum numbers j and l. Now en is equal to this quantity, therefore m e square by 32 pi square epsilon 0 h cross square 1 by n square is en. Therefore we get en of 1 is equal to, n1 means the first order correction to the nth energy level is equal to this quantity. So the correction in energy or the spin orbit interaction energy is ESO, that is En of 1, the first order correction to the nth energy level of hydrogen atom due to spin orbit interaction. It is equal to En square, actually this is En square. En square, that is the nth energy level of unperturbed hydrogen atom divided by mc square, that is this one mc square. And there is one n is here, n into j plus 1 minus l into l plus 1 minus 3 by 4 by l into l plus 1 by l into l plus half into l plus 1. So this is the correction to the nth level of due to the spin orbit interaction. Here also we can see that the spin orbit interaction lifts the degeneracy of hydrogen atom. Now all the states into the same n value is not having the same energy because it depends on L and J. Now for L equal to 0 state, if L is equal to 0, then total angular momentum J is equal to L plus S becomes L only, or J is equal to L plus S becomes S only, because J is equal to S because L is equal to 0. In that case, both the numerator and denominator becomes equal to 0. It means that there is no spin orbit coupling in L equal to 0 state. L equal to 0 means for S orbitals there will be no spin orbit interaction. But there will be another correction called Darwin term for L equal to 0 that we have not considered in the syllabus. So the complete fine structural correction of hydrogen atom is the relativistic correction plus the spin orbit coupling plus the Darwin term. Actually we are not considering the Darwin term. So here we consider only the two terms, relativistic correction and spin orbit correction. Both of them are of the order of En square by mc square. We have the relativistic correction as minus En square by 2 mc square into 4n by n plus half minus 3, and the spin orbit correction is En square by mc square into the quantum numbers. So we get, so the complete fine structure correction of hydrogen atom is sum of these two, that is EFS, complete fine structure at the first order level. It is En square by 2 mc square into this one, that is the spin orbit correction plus the relativistic correction. Now in hydrogen atom there are two cases. The total angular momentum J is equal to L plus or minus half, or L is equal to, the orbital angular momentum L is equal to J plus or minus half. You can take this L here, so plus or minus half goes here. Here there is a J, total angular momentum J, so L is equal to J plus or minus half. In both cases, we get the complete fine structure of hydrogen atom as given by the following expression. So the derivation is given in another PDF. You refer to that PDF for the derivation of this equation. So the total fine structure constant of hydrogen atom is given by this expression. Now, combining with the Bohr formula for the gross structure of hydrogen atom, we get the grand result for the energy levels of hydrogen atom with fine structure as ENJ is equal to En plus EFS of 1. En is the energy levels of unperturbed Hamiltonian, that is called the gross structure or Bohr energy levels, and EFS is the correction due to the fine structure due to the relativistic correction plus spin orbit correction. And remember, this expression is valid for all levels, whether L equal to 0 or not. We have already stated that for L equal to 0 state, there is no spin orbit coupling. But that for L equal to 0 state, this expression is valid because there is another correction from the Darwin term. So if we consider Darwin term, this expression EFS is valid for all levels, whether it is L equal to 0 or not 0. So we can see that this expression is valid. Spin orbit coupling is absent in L equal to 0 state, but the derivation of EFS, this expression is valid for all states. Therefore, the total energy En minus 2 En by mc square to En by j plus half minus 3 by 4. So En can be taken as, we get Enj is equal to En into 1 minus 2 En by mc square into En by j plus half minus 3 by 4. Now En is equal to minus alpha square mc square into 1 by m square. Therefore, this Enj is equal to En into 1 plus, this becomes, En becomes minus, so minus into minus plus 1 plus alpha square by m square. Here En is alpha square mc square, that is mc square cancelled, 2 and 2 cancelled, so remaining will be alpha square by n square into n by j plus half minus 3 by 4, where En is minus 13.6 by n square electron volt. So this is the total energy levels of hydrogen atom, including the Bohr energy level plus the fine structure energy level. So this is the energy level, complete energy level including the fine structure. So the fine structure breaks the degeneracy in L. That is, for a given En, the energy Enj is different for different En. But levels into the same N and J are still degenerate. For example, 2s half. 2 is the principal quantum number and half is the total angular momentum quantum number. Half, 2s half and 2p half. Both of them have the same energy even in the fine structure, but they will be different if we consider the hyperfine structure and lamp shift. So fine structure constant, fine structure also keeps some energy levels still degenerated. The degeneracy is not fully broken in fine structure levels. So the fine structure of hydrogen atom is given here. The Bohr levels are n equal to 1, it is minus 13.6, n equal to 2, minus 3.4, then n equal to 3, n equal to 4, etc. Now, fine structure, if we consider fine structure, then 1s half, n equal to 1 means there will be only s, L equal to 0, therefore 1s, there is no splitting, it comes in the downward direction, 1s half. Then this n equal to 2 has 2s and 2p. 2s has no splitting, there is only 2s half, but 2p has splitting, there will be 2p half and 2p 3 by 2. Out of that, 2p half and 2s half are on the same energy level, but 2p 3 by 2 is having a higher energy level. And this n equal to 3 will split accordingly. Out of that, 3s half and 3p half have the same energy in the fine structure, but if we consider the lamp shift, there will be splitting for the s, And if we consider the hyperfine structure, there will be further splitting of the fine levels. So this is up to this one is the fine structure of hydrogen atom. So after passing through this video, answer the following questions. What is spin orbit interaction? Evaluate the commutators. L dot S L, that is the operator L dot S with the angular momentum L, spin angular momentum S, then total angular momentum J, then L square, S square, and J square. Then Y spin orbit operators S square and SZ commute with all spatial operators. Now here in the calculation of correction due to the spin orbit coupling, we used the eigenstates of NL, J and J as the unperturbed states. Is it not possible to consider NL, ML, MS as the unperturbed states? Yes, it is possible. So what is the difficulty in using those states? Draw the energy levels of hydrogen atom including fine structure. So thank you for watching this video.